Are you able to see the screen?
Yes, sir.
Okay, good. Yeah. So it is represented as in decimals. Okay. So decibel is 10 log based on P2 by P1. That's what we represent. These things we can calculate easily. These things are known because in decimals we can we need not normally when you amplification or attenuation, either you have to divide and multiply in practical terms, but when you convert into decibel terms, it's easy. You can go on addition or subtraction. That's the advantage of using decibels. Now, one example, port 1, port 2, here port 1 to port 2, it is attenuation is minus 3 dB, whereas port 2 to port 3 is 7 dB amplification, and port 3 to port 4 is minus 3 dB. So overall, if you see how much, signal, what happened to signal? 1 dB gain here, 1 dB gain. So dBs converting to dBs, this is the advantage. Okay. Now sometimes when the signal is very small, then we also represent it as a dBm. Okay. So milliwatt power. That's how we take it. These examples also just go to quickly. The loss in a cable is usually defined in decibels per kilometer. So per kilometer. If the signal at the beginning of a cable is minus 3 dB, minus 0.3 dB per kilometer, has power of 2 milliwatts, what is the power of the signal at 5 kilometers? So this can be calculated easily. The loss in the cable in decibels is 5 kilometers per kilometer. This is 0.3, so it becomes minus 1.5 dB. Right? So minus 0.5 dB, and original what is the power? Original power is 2 milliwatts here. Okay. So at P2, what is the power? So using this formula, you can calculate dB equal to 10 log 10 of P2 by P1, which is equal to minus 1.5. So when you compute this one, it becomes P2 becomes 1.4 milliwatts. So 2 milliwatt input power has become 1.4 milliwatt. That's how we can compute this. Okay, and so composition, when you decompose, it looks like this because it has this thing. Okay, now distortion. Second impairment we talked about distortion. So when you take composite signal, we said this is combination of multiple sine waves. Okay, so when these sine waves are, because they are different frequencies, when they are propagating through the channel, all need not travel at the same speed or reach the destination at the same phase. These are, please look at the phase of each of them. So, and received signal phase, they are different because these different frequencies are reaching at different phases at the receiving end. When you integrate all these things, the shape of that will not be same as original shape. You will not be able to get it because this phase of different components of these frequencies, composite signal, is getting changed here when it reaches at the destination. Because the change in the phase, when you integrate all these things and compute composite signal, the shape of that will not be same as this one. So this difference is called distortion. So this happens because of propagation characteristics of the medium. Propagation characteristics of the medium. Now noise. So noise is unwanted signal getting added in between somewhere. Okay. This noise also sometimes it can boost or it can cause attenuation also. Okay, like this. This is called noise. So that means there are three types of impairments: attenuation, amplification, or one of them, and distortion, noise. Okay. So these things also the power of the signal is 10 milliwatts and the power of the noise is 1 microwatt. What are the values of SNR? So SNR is nothing but signal to noise ratio that can be represented, that can be converted into dBs and can be represented as a dB. Here in this case, 1 microwatt is the noise and the signal strength is 10 milliwatt. So that means 10 milliwatt by 1 microwatt. And if you convert into decibels, it becomes 40. Okay, and this is also another example you can see, and Okay, now coming to okay, another 2 minutes we'll take, and then we can break and go to the next class. So data rate limits, very important consideration in telecommunication is how fast we can send the data. So data rate normally depends on bandwidth available. So because data rate also related to bandwidth available and level of the signals we use, because as the number of levels used, the number of bits represented for each level also varies. So based on that, number of bits increases, so it also impacts data rate. The quality of the channel, okay, and similarly SNR value. So all these things factors will have influence on data rate. Okay, so here if you see noiseless channel, when this is a perfect channel, normally we use Nyquist bit rate for calculating how many bits it can uh, uh, transmit per second, or what is the maximum data rate or capacity it can handle. Similarly, noisy channel. There is another scientist channel. He has determined what is the capacity the channel can handle it. Okay. So these two, based on these two, we can really practically calculate what is the data rate maximum we can utilize it. One defines ideal case, noiseless. Other one is noisy channel. Okay, increase the levels of signal may reduce the reliability of the system. Okay, so 1 minute, we'll go to this thing and see. And using the Nyquist criteria, how do we calculate? We calculate bit rate equal to 2 bandwidth and log of number of levels to the base 2. This, I think all of you are familiar with this one. So this gives, when you say number of levels with base 2, log of number of levels with base 2, it gives number of bits required to represent each level. Okay, that number of levels multiplied by 2 into by this one bandwidth. Bandwidth is 300 kilohertz here. Taking 300, sorry, 3000 hertz, 3 kilohertz multiplied by 2. This one. Okay, so that's how we can compute the capacity bit rate that can be handled by the channel using Nyquist method. Whereas if you go to the okay, this is another example where we have 4 levels. Then we go to the next one. We use Shannon method, that also we'll see. Consider an extremely noisy channel in which the value of the signal to noise ratio is almost 0. In other words, noise is so strong that the signal is faint. But the channel capacity is 0. So this is calculated using the channel formula, or for noisy channels, calculate capacity equal to bandwidth multiplied by log of 1 plus SNR with a base 2. Okay, right? With a base 2. So the only thing you have to convert is when SNR is given into decibels, these things have to be converted to actual value when you are computing capacity. This you have to keep in mind. B is bandwidth in hertz multiplied by log 1 plus SNR. SNR normally is given dBs, right? The dB you have to convert into numerical value and then plus 1. Then you have to take log 2 of that value, then multiply by 5. Then you will get it. So this example you can go through it. That's how it is done. Okay. Now I think let us stop here and see remaining things in the tomorrow's class. Okay. Right. So come at least 2 minutes before every day to the class so that we don't miss and we can start early class. Okay. I'm stopping here. Right. Then we can go to the next class. Okay.